So welcome back to the second part of this video. If you've not had a chance to watch the first part, please do check it out, as that's going to explain exactly what we're doing and a step-by-step guide before we go into this video. So please do check it out. So if you've checked it out already, welcome back. Let's begin with this example. So, as we've discussed in the previous video, we're going to use these 5 steps to work out the current and voltage drops across each resistor. Now let's begin with that. So the very first step, we're going to mark each resistor or each power source and resistor with positive and negative signs. Remember the key that I discussed in the previous video. Let's begin with that. The short terminal of the battery is negative and the long hand or the long line is positive. So let's do that with each power source. So that's negative and that's positive. Now remember, current flows from negative to positive, and that's our assumption. So if negative terminal is here, that means the current's going to flow in this first loop, which is A, B, E, F, B, in a clockwise manner, which is going to be this way. So that's going to be negative. That's first negative, that must be positive. The current flows downwards, so that's negative, that's positive. Now in this case, negative is here, positive is here. How do we get to negative to positive? We can't jump across the battery, we must follow the loop. In this case, this is counterclockwise. So let's add that in. That's clockwise, that's counterclockwise. So that's negative. First point of the resistor is negative as we meet it, that's our assumption. Again, as we go down, this is negative, that's positive, and we must go positive back here. So what else have we noticed? Well, that's going to be the second point. Indicate the assumed current directions for all branches. Now we've said for the first branch that's clockwise, and for the second branch that's counterclockwise. But as the current flows from this battery or power source to here, and then from the current flows from this battery to this point here, at point B we've got 2 sets of currents. So remember what I talked about. The current entering the node must equal the current exiting the node. So what can we say? Current 3, I3. We've got first current of going I1 and then the second current I2 going counterclockwise. We can say I3 is equal to I1 plus I2. So that should all be in continuity. So let's now begin with the first loop. What I'm going to do is just quickly clean up the screen so we can write down our equations. So let's begin with the first loop. And that's going to be A, B, E, F, A. The reason why is because as the electrons leave the negative terminal, the first point in the circuit is A. So we're going to say that's A, B, E, F, and then we're going to close the loop by adding A back in. So now let's look at identifying the loop, which we've just done, and using Kirchhoff's voltage law to write the equation for each loop. So as the current leaves the negative terminal, the first point of R1 is negative, and that's going to be using this diagram on the right hand side. Remember the voltage law, it's going to be negative because the first point of contact in that resistor is negative. So let's say the voltage across R1, which is negative, and then as we go through this loop, the first sign of R3 is negative, so we can say minus voltage across R3, and then if we close the loop, which is following it back round, we've got V1. The first point of contact is positive, so we can say plus V1 is equal to 0, and that must equal 0 for continuity. So then if we use V equals IR, which is going to be step 4, let's replace the voltage in this equation. So we can say that I, in this case, we assumed in the first loop is equal to I1, and that's across resistor 1. So that's going to be, and we know that the resistance value is 24, so therefore we can say that minus 24 I1, and for resistor 3, we've got 12 ohms, which is the resistance value, and we've got I3, the combination of I1 plus I2. So that's 12 I3 plus the voltage is 168 is equal to 0. And using the equation of I3 is equal to I1 plus I2, let's substitute that back into I3 here. And we'll clean up the equation as we go along. So we can say that minus 24 I1 minus 12 I1 plus I2 is plus 168 is equal to 0. If we expand that through, what do we get? So we get, let's just put 168 on the positive on the left hand side, minus 24 I1 minus 12 I1 minus 12 I2 is equal to 0. Collate the common terms, so that's positive 168 minus 36 I1 minus 12 I2 is equal to 0. So if we then find a common factor of 12, we can divide through by 12, and we can say that 14 minus 3 I1 minus I2 is equal to 0. And that's going to be our first equation. And that's that loop here. So if we repeat this for the second loop, again, the negative terminal coming out, the first point of contact is point C, and then it's going to be B, E, D. Let's close the loop, C. So that's going to be loop C, B, E, D, C. Again, let's now replace this with the voltage drops. So that's going to be leaving the negative terminal. The first contact of R2 is negative, so that's negative voltage of R2, negative voltage of R3, plus 42 is equal to 0. So therefore, replacing V with IR, we can say that negative I, which is I2 of R, as we've assumed here, and we've got 6 ohms, so 6 I2 minus 12 I3 plus 42 is equal to 0. So therefore, we've got minus 6 I2 minus 12 I1 plus I2 plus 42 is equal to 0. If we simplify that, we've got minus 6, expand that through, minus 6 I2 minus 12 I1 minus 12 I2 plus 42 is equal to 0. Collate the like terms, we got 42 minus 18 I1 minus 12 I2 is equal to 0. Then we can divide this through by 6, I believe is the common factor here. So we can say that's 7 minus 3I1 minus 2I2 is equal to 0. And therefore, that's going to be our second equation. Now, can we see we've got two equations with I1 and I2 unknown. So that's two equations with two unknowns, and we can work through exactly what we're doing. So what I've done is just clean up the screen and put two equations we've just worked out here. Now what I'm going to do is use the method of substitution to work out I1 and I2. So what I'm going to say is, from equation 1 we can say that I2, by bringing it to the other side, is equal to 14 minus 3I1. Then I'm going to say, let's substitute this 14 minus 3I1 into equation 2. So therefore we get 7 minus 3, 14 minus 3I1 minus 2I1 is equal to 0. If we expand that through, we get 7 minus 42 plus 9I1 minus 2I1 is equal to 0. If we clean that through, what we get is minus 35 plus 7I1 is equal to 0. Therefore, I1 is equal to 5 amps, is substitute I1 is equal to 5 amps into I2 to work out that. So that we can say that therefore I2 is equal to 14 minus 3 I1, which is 5. So therefore I2 is equal to 14 minus 15. I2 is equal to negative 1 amp. So what that negative sign means is that our assumption of current going counterclockwise is actually wrong, and it's going clockwise indeed. So therefore we can say that I3 is equal to I1 plus I2. So therefore I3 is equal to 5 minus 1, which is 4 amps. And now what we can do is work out the voltage drops. So that's going to be using Kirchhoff's law of V equals IR, and we can say that the voltage drop across resistor 1 is going to be I1 R1. So we know I1 as to be 5 amps and resistance is 25, so therefore 5 multiplied by 24 is 120 volts. Voltage across 2 is equal to I2 R2, and we don't take the negative, we take the positive current, so that's 1 amp multiplied by 6 ohms, which is 6 volts. And then finally the voltage drop across R3 is equal to I3 R3, which is 4 amps multiplied by 12, which is 48 volts. So hopefully you found that somewhat useful. If you did, please consider liking and subscribing. Please do leave a comment down below if you need any additional help, or if you would like to see something specific. If not, I'll see you guys in the next video. Take care.